Okay, so this is chapter 10, and we're talking about using solvents as reagents. Okay, and so we've actually seen this a few times now, right? Specifically, we've seen here methanol. That is what listed as a what? That's listed as a solvent, right? Reagents would normally be listed up here, right? However, you can use a solvent as a reagent, right? What's the difference between a solvent and a reagent? How much do you know?
The amount present?
The amount present. Exactly. That's perfect. Yeah. It's so when I'm putting a solvent, I put a bunch, right? I'm putting excess plus, right? When I'm putting a reagent, I'm being careful about that. I'm putting a specific amount, aren't I? Okay. And so you may have noticed that in the reactions we've done in lab, some of these don't really require very specific measurements, and they're just like, throw in a milliliter. And some of them we have to take the syringe and carefully measure out, right? Yeah. And typically that's the sort of difference you'd see when you're putting reagent amounts in and when you're putting solvent amounts in. Convention 3. This is going to be using numbers to combine reactions that are carried out sequentially. So each reaction should have its own numbering if you're going to do this, and the reagents and condition necessary to carry out each reaction will then be written above and below the reaction arrow. This is for things that are going to be pretty simple reactions, one after another, but you don't want to have 20 different steps, okay? You can shrink it down to then 10 steps by doing this, right? And you can number off the steps. This is usually for stuff that doesn't require very complicated, like tons of different reagents. It doesn't require very specific reaction conditions. It's for relatively simple stuff. Okay, and so what are we looking at here? Does this reaction require two different reagents in one step? You're looking at two steps to the reaction, aren't you? So the first thing you'd do is you'd put this, which is your substrate, in with this. You would run that reaction. And then you would add this to that reaction. You may have to do a little bit of purification between. It would depend on the exact synthesis. Okay? But these are the different steps of the reaction. Is that making sense?
So those are both reagents?
Yeah, those are both reagents. Yeah. And you can tell this because of the numbering. Okay? When it's a reagent plus a solvent, i.e. the conditions, there's no numbering because that's all one step. Is that making sense? Can you see the difference there? Okay. And you can go like 1, 2, 3, 4, 5, 6. You could go very, very long on this. And it would just mean that these are all simple reactions. You would do one after another. Okay? All right, so these are conditions in a sequential reaction right here. If you're going to do a sequential reaction, this would be your reagent. You would then put a slash, and then these would be conditions. So in this case, we have a solvent we've listed for each of these, haven't we? Okay, and again, these is the reagent slash conditions, which is water. So the second one's actually be doing an aqueous solution, isn't it? Can everybody see it okay? Okay, can we read that? All right. And how can you tell the difference between which one you're looking at? The numbers, right? Numbers and slashes. Okay. Okay. Now, slashes are the most common. You can actually separate the reagents by commas as well. So if you see commas, that may also be the same thing, okay? And you can always tell because it'll be reagent, comma, next thing. So for each of the reactions you encounter, you should ask yourself the following questions. What functional groups in the reactants are involved? What functional groups are produced in the products? What are the major structural changes that occur? So for example, here we have an alkyne starting compound. Here we have the reagents and reaction conditions listed. X here means we're using some sort of halogen. Okay, that's a very common method for saying any halogen we want to use. Okay, you don't always have to have the same halogen actually, because all the halogens there, Cl, Br, I, those are all good leaving groups. Okay. So the next part, these are actually the key electron-rich species. Where do we see that, by the way? That's this, right? That's the one that's going to act as your nucleophile, right? This one right here is the one that's going to act as the electrophile for this, right? And so we're attacking with that. This is the alkyl halide right here. That's the key electron poor species. That's that one that has a slightly positive charge, right? This is an SN2 reaction in this case. And so we have just looked at an SN2 reaction that's going to happen, but we've broken it into several steps to set it up first. Okay? And so that's what we're actually looking at. Okay. So these are some examples of two reactions types in a synthesis. So here we have a functional group conversion. So here we see that we have a double bond, right? We're going to set this reaction up to change that functional group over to an epoxide. Epoxides are more reactive. Can we see that? And so we've set it up to be something very reactive that we can then react a group we want to add to it. Okay? And so we're going to then have here our carbon-carbon bond formation. This is the CH3 MgBr. Remember, that's a way to get a nice positive charge on that CH3, a way to get that, negative charge on that CH3, so that we can then attack that carbon on the epoxide, right? Okay. And then we need to follow that up with these conditions here, which is water and acid. Okay. Can anybody tell me why we would have to follow that up with the water and acid?
Is the acid the conditions? Is the comma?
Yeah. This is actually a set of conditions right here. Technically, the water could also act as part of the reagent system. What we're actually doing here is when we do this first reaction, we're going to form this right here. And then we need to add NH plus, right? To get the alcohol. So that's actually the protonation step right here. Mm-hmm.
You may have already said this,
Mhm.
but since they are like two separate reactions or like steps in the reaction,
Mm-hmm.
would you draw out like the intermediate step, or would you just go on like how they have it, just having it basically?
So for these reactions, you don't normally need to draw up the mechanisms. This is more like how you write it so that somebody could follow it as a recipe. So, like if you were going to give somebody instructions on what to do in lab, you wouldn't want to give them a mechanism, right? They would look at that and be like, what the hell am I supposed to be doing right now? Yeah, kind of like I never give you mechanisms in lab, right? So if you ever look at the first pages of those labs I give you, they have stuff that looks like this. Yeah. And the reason for that is this is what you would give somebody that like, okay, I want you to go and do these reactions and get me this final product. And then the person you give it to is then going to break that down into the procedures that I gave you. And so then you're going to go, okay, I need MCPBA. I'm going to need to figure out if I need to heat that or how long I'm going to have to do the reaction for it. And they'd figure that out.
Gotcha.
And then they're going to get this epoxide, and that'll require a little bit of purification usually. Okay? But they know they need to get that epoxide. They'll test it. Yeah, I got the epoxide. Cool. Okay? And then the next step they're going to do is they're going to take a CH3 MGBR. They're going to have to generate that in solution. And then they're going to let that reaction go. In this case, normally, if you do not need to do a purification in between the steps, that's where you would do this 1, 2, 3 thing. Is you're not having to purify the product in between. And in this case, we would end up with an alkoxide. And this is the step that actually gives us this alcohol right here. And so you actually can't purify in between. And that's one of the reasons you'd want to do that, where you just do 1, 2. We're getting now a product we could purify. And so this is the checkpoints usually, is where you actually list a product so that you can purify a product, take a GC of it, take an infrared of it, and check, did I get that product? Does that make sense?
Yeah, that makes sense.
Yeah. And then you can go on to another step. In this case, we can go on another step, PBR3. Okay. And we can go ahead and form the bromoheptane by doing an exchange, substitution with the OH there. And this is going to, again, set us up so we could do another reaction. Is that kind of making sense? Yeah. Yeah. And you can think of these syntheses as a sort of high order outline like you would do for a paper. Does that make sense? They're that high order outline, and then you'd fill it in with the procedure I give you whenever we do labs, of like heat it this long in the acid. Okay. Did that make more sense for everybody? Okay. Okay. And that's the best thing to think of these. Now, when we're writing out these syntheses, these are actually the high order instructions that you'll use to generate those procedures to actually do the synthesis, right? Okay. And there'll be steps that you follow. This one then gives you the negatively charged cyanide here to do that substitution with the bromide. And that's the ultimate product we're actually generating here. Okay. Yeah. By the way, if you ever go to grad school, your advisor would give you this and say, make it. Okay?
So under the letters like A, B, C, D, what is chapter 13, 11, and 10?
Those are the chapters the reactions were in.
Oh,
Yeah. Yeah. So if you were to look for those specific reactions and mechanisms, that's where you'd find those. Yeah. In this case, this is what's called click chemistry. I'm just listing the reaction and giving you the product. That wouldn't actually be enough information to do the reaction and get a good yield. You would actually have to look up the specific reaction and then figure out under what conditions would give me a good yield. Well, that's the major product. Does that make sense? Yeah. I've just given you the extra information. If you go, how the hell do you do a PBR reaction? What's that? You can find it easier.
So it's kind of like an ingredients list, sort of.
Yeah. Yeah, I'm just giving you references. So if you look at this and get confused and go, what is this? You can actually look that up. Okay. And then the A, B, C, D is just so you can keep track because this goes like that, right? Yeah. And that's a little confusing. Yeah. Okay. So let's talk about some of the options and limitations in your syntheses. So the ether formation by a Williamson synthesis and condensation. Now, see this name here? Williamson? Okay. This is what's referred to as a named reaction, right? Has anybody ever heard of named reactions before? No? Okay, that's fair. If you actually decide to go into organic chemistry and become like an organic chemist, which is kind of like the artist of the chemistry world, okay? It's actually kind of an interesting career. I personally would not want to ever do that. It is. It drives me nuts. But like sitting there all day making like adjustments, small adjustments to my reaction conditions would just drive me nuts. And that's a lot what you do. So named reactions are something that an organic chemist can look up and use as sort of like building blocks. Okay? They have a bunch of information that's associated with those named reactions, and you can actually look them up. There's something called organicchemistryportal.com and a variety of websites like that. And what they have is actually lists of named reactions with, on the top, the functional groups you can start with and functional groups you can end with. And you can use them like little building blocks. And then the conditions under which these work well. Okay? And so you're going to start seeing named reactions. And the reason you're seeing these is that if you were to do this professionally as an actual synthetic chemist, this is the easiest way to deal with it, is using these named reactions and clicking them together to get what you finally want. Okay? It actually is not as hard as you think. It's a very much a grad school thing, though. Okay? Or an actual professional organic chemistry thing. You're going to see the hints of it. I'm not really going to go into a lot of detail on it. Okay? So, this right here is the Williamson synthesis and condensation. This is actually the steps here. So here's steps 4 and 5 here of that over. And this is the starting compound class. We have the primary alkyl halide. This is the reagent that you typically use to do this, including the reaction conditions if there's anything special. And this is the compound class that's formed, which is the ether. Why do I keep calling these compound classes, by the way? So see these R's? I can do this to a whole variety of compounds, right? Those R's could be a huge 20 carbon chain with all sorts of different things on it, right? I don't care. All I care is that it has an alkyl halide in there, and I'm turning that into an ether, right? Okay. And so I can do the same reaction with mostly the same conditions for hundreds of different actual compounds, right? The only thing I care about is that I'm starting with this functional group and I'm ending with this other functional group, right? Kind of like Lego sets, right? There's hundreds of different Lego pieces that could snap together, right? Yeah. All that matters is that you have the little male and female connectors, right? Okay. Okay. This X right here, what does that X usually mean?
Halogen.
Yeah, that's the halogen, ClBrI, okay? Good deal. Now, notice that this is specifically for a primary alkyl halide. Why is that specifying primary alkyl halide? Is that important? Yeah. Remember our mechanisms, primary versus secondary, changed a lot, didn't it? And tertiary certainly would really change this, wouldn't it? Okay. Now, this is some of the more additional information. Really good books will have this additional information. Bad books will just have this part and nothing here, okay? Because they'll compact down the list and not want to print more. This is quite important because it tells you things like the key electron-rich species that you're going to have to support. This tells you things like, will this work well with aprotic solvents and protic solvents, right? Yeah. Which is part of the stuff we've been learning. This over here is the key electron pore species. And so this tells you things like if you have another functional group that looks like that, this is going to attack those. Okay? This is the type of reaction right here, the SN2 reaction, the elementary step that is most important here. Okay? And by the way, your book is really, really nice to you and actually then goes on to tell you where you can find these things. Okay? In case you go, what in the world? What is the SN2 reactions again? I don't know. There you go. Okay. All right. So this right here would be your next deal. This is an alcohol that reacting. This is under acidic conditions with heat. Can everybody see it okay? And we would produce an ether in these reactions. Okay. All right, so this is the Williamson ether synthesis in full. So we're going to start with a 1-bromobutane, and we're going to add this alkoxide here. And what we're going to get is we're going to get a dibutyl ether out of this. Okay, that's the entire reaction. Notice that we add this to that, we get that product, right? High level instructions. Okay. Okay, the mechanism is down here. Right? If you're going to provide a synthesis, you don't need to provide mechanisms necessarily. Okay. So the mechanism is going to be, we have this alkoxide, everybody sees that okay, right?
2-pentanol can be synthesized through various routes. One common approach involves the reduction of 2.
What the hell? The AI decided to add to it, I guess. The AI is getting really pushy, isn't it? Yeah. We're like this close to Skynet, except Skynet's just annoying. All right. So the alkoxide's going to attack. What sort of mechanism is this again? An SN2 reaction, right? And so the alkoxide attacks. The leaving group, which is the Br here, leaves. And this is going to go ahead and give us this linkage right here. Can everybody see it okay? That's the new bond, the SN2, the substitution we did. Okay. All right, and that is the final product here, isn't it? Can everybody see that? Okay. Okay, so what's the next step? Well, that's the next thing we're going to need to talk about here is the condensation reaction. So in a condensation reaction, two larger molecules are going to be joined at the expense of a loss of a smaller molecule. And specifically in a condensation reaction, this is typically going to be water. Everybody see where you got the name? Yeah, condensation, losing water, right? Okay. Okay, and so right here we have our alcohol. This is butane 1-ol, or 1-butanol, if we're doing the old IUPAC methodology that made us some sort of sense on saying it. This is going to be acidic conditions with heat. Okay. Okay. And what we're going to get is we're going to get our dibutyl ether here, 91%, and we're going to lose water. All right. So, can anybody try to guess the mechanism for this? Okay, we're under acidic conditions, right? So, what's likely the first step that's going to happen? We have something that's can act as a base. We have acidic conditions. We're going to do one of those proton transfer steps, aren't we? And so the first thing we're going to do is we're going to generate H2O plus, aren't we? Okay, so first step, proton transfer step. Is everybody comfortable with that step? Okay. Nobody's getting lost at all? Fantastic, awesome. Okay, so once we do that proton transfer step, we have a really good leaving group, don't we? than H2O plus, which would give us water is leaving. Okay. We also have more of our substrate. And that substrate can act as an attacking species, can't it? See, it's a nucleophile. It's not a great nucleophile, but it normally would be a nucleophile, right? And so it's actually going to be another one of those substrates, the attacking species. Our water will be the leaving group in an SN2 reaction. And this is going to give us this, which is the protonated species, right? That protonated species makes a lot of sense because we're in acidic conditions, aren't we? Okay. And so then water is going to act as our base, deprotonate that protonated species, and we'll get our final product after that final proton transfer step. Okay. Is everybody good with that so far? Okay. Okay, you will notice something kind of unusual about this entire reaction, right? If we looked at the overall reaction, what did you notice about the overall reaction? What was the product? Water. What's the product here? Hydronium, yeah. So in this, we've represented our acidic conditions right here, okay? And it goes without saying that water, when we're talking about acidic conditions, we can either think of this as we used up the acid and then we regenerated it, in which case there's actually a catalyst, right? Or we can think of it that we understand we're acidic, we can just represent water right here, okay? Because that's the only thing that's disappearing off of these, is water. All right? Please don't get confused by that. Okay, so let's talk about some of the limitations of the ether synthesis with condensation reactions. So what reactants can come together to give these products here? What if we don't have a symmetric product? So we had a symmetric product right here, right? And so it didn't really matter which of the substrates, which of the reactants got attacked in that proton transfer step, did it? We don't care, because it's going to generate the same thing either way, right? What about here? That's not symmetric, is it? No. So that means we have to have two different substrates that have alcohols here, don't we? Okay. Are we going to generate just one product out of this? No, we got two alcohols, right? That proton transfer can happen to either alcohol. In which case, we're setting up the two different alcohols to both be reactive, aren't we? So what can end up happening is we can get our desired product. Yeah, sure. No problem. Okay. But we're also going to get where the alcohols react with themselves, right? Rather than the other alcohol. Because there's not like a special selecting mechanism that's happening that only one alcohol can act as the substrate, only one alcohol can act as the attacker, right? They can all act as attackers. They can all act as the substrate, okay? Some of them might be a little bit preferred, and so we may not get equal amounts of each of these. But we're going to get 3 different products here, and you're going to, if you were doing this, you'd have to separate those products to get the desired product out, right? It wouldn't just automatically give you what you want, okay? So this is one of the things you gotta be very careful of when you're talking about these condensation reaction ether syntheses. This right here is the symmetric and unsymmetric ethers. They both can be produced via the Williamson ether synthesis. Right here we actually see an example of a asymmetric ether that can be produced. On the other hand, though, you can't produce every single ether that's possible in every single way of the Williamson synthesis, right? So what would happen if we started with this right here? Can that undergo an SN2 reaction? No, we've blocked out the SN2 product, haven't we? And so that wouldn't give you the ether at all, would it? No, that's going to give you a dang double bond. That's Not an ether synthesis, is it? Yeah. So your choice of substrate actually is very meaningful in a Williamson ether synthesis, okay? You actually do have to be very careful about it. Okay, so let's devise a Williamson ether synthesis that would produce the ether shown here. This is that intended product from that previous slide. See, it's just previous slide. Is there a way we could do the Williamson ether synthesis rather than a condensation? Is there a small change we could make which would make this Williamson ether synthesis give us the desired product? Okay, mirror bromine by... Okay. Did we have to have this one be the alkoxide and this one be the bromo? Could have we swapped functional groups here?
Yes.
Okay, and that would have given us a primary substrate, right? We can do primary substrates. That works. And then that would have given us a tertiary alkoxide, wouldn't it? Which also would work, wouldn't it? Yeah. And so the way you can actually fix this is you could have just done the ethane for the bromide and then done the tertiary alkoxide instead. And that would have given you the product. That would work fine. So it's not actually difficult to fix. You just have to start off with slightly different reactants, don't you? By the way, your reactants is one of the most changeable things about reaction. Okay? What's the one thing you can actually have control of in a reaction? What goes in there, right? And so when you're looking at these reactions, and you're going to learn this in retrosynthesis, the next chapter is where we're really going to hammer in on this. The one thing you really have control of is that you can buy small substrates, you can buy your reactants, and you're the one that gets to choose which ones goes into that, right? Okay? There's going to be some limitations to that, and you may have to get fancy to tap dance around issues. You see me do that a lot this semester because of various limitations with what we actually had available to us. But that's the one place that you get some sort of choice, right? By the way, a lot of those things I was able to order later. I just couldn't get them in 2 weeks, right? Yeah. And some of them I managed to get in 2 weeks. Woo! Okay. If you haven't joined already, please do join. Okay. So how can we design the synthesis of the unsymmetric ethers shown below? What would be a way to design this? So we need to join these ethers together, right? Okay. And if we want to use the Williamson synthesis, how do we do it? Does it make sense to attack? Okay, so when we look at these final products, right? See, you could have either this bond is the one break that you made, or you can have this one being the one that's made, right? Okay. And so the one that you're making has to have the leaving group there, doesn't it? Now, when we look at these in terms of which one would be more beneficial to have as the carbon that gets attacked, which one's going to be the better one? A primary, secondary, or tertiary carbon to attack? You're going to want to attack a primary, right? It's more exposed. The reaction is going to go faster, isn't it? Okay. A secondary is going to be slower than a primary in terms of an S&2 reaction. And a tertiary is not going to happen at all, right? Okay. So when we look at these, this one is the one that makes the most sense to do the alkoxide on, because we don't have to attack into a secondary carbon, right? This one, on the other hand, is a primary carbon right there, isn't it? And so it makes more sense to have our leaving group, because that becomes the place we have to attack, doesn't it? Can everybody see that? Okay. And so in terms of Williamson synthesis, this makes the most sense to use as substrates to make this product right here. Okay. Okay, let's look at the functional group transformations. So again, we have our alcohol here. We have here the acid, and we have the alkyl halide right here. These are some different options we could use in terms of transformations. So here we actually have the alcohol coming off the benzene. If we use HCl here, this would actually give us that H2O plus leaving group, and then the chloride can transfer over. Can everybody see that okay? And so we could actually make that previous step. Over here is how we can make that other step. So, how do you get the alkoxide? Do you think you're always going to be able to buy that? No, that's not going to be something you're always going to have available, okay? So, oftentimes what's going to happen is you're going to need to take the alcohol, you're going to need to use a very powerful base, and that would generate the alkoxide, okay? And this is your powerful base right here. That's that sodium hydride. And so we generate the alkoxide. We normally would represent that as Na, and then this alkoxide right here, right? In this case, we're just dropping the Na because we don't need that in the synthesis instructions, because we're putting this step to make. Okay, so this is what the final synthesis would look like if we don't just freely have everything available. Okay, so here we have that benzene alcohol right there. We're using HCl to generate the chloride. And then we're going to use the NaH to take the alcohol right there and generate the alkoxide. We'll have those together then. This is then going to do that SN attack, SN2 attack, right? And that's going to give us our final product. And so that would be a full synthesis for this. Anybody get lost in it? No? Okay, fantastic. Okay, so how can we convert alcohols into alkyl halides? Well, PBr3 and PCl3 both work very nicely. Okay, and so this is one method of converting into a bromide or chloride. This would be concentrated HBr under heat for 4 hours. Everybody read those instructions okay? Fantastic. Remember, this is going to be this mechanism down here. So we're going to have a proton transfer step first. Everybody see that okay? And then we're going to lose the H2O plus leaving group as the Br minus attacks. Okay. This is why one of the reasons we need concentrated, by the way, to do this, is because we need quite a bit of this Br minus, don't we? To actually do this reaction. Because it's an SN2 reaction. Concentration matters. And so then we get the bromide. This now has set that up to be a better leaving group to do another synthesis with, right? Yeah. And we have something we could purify, we could stabilize, we could actually get a decent concentration of. Okay, so let's talk about some unwanted side reactions here and some of the stereochemistry and carbocation intermediates for this. So if we use concentrated HCl here, and this can actually do the SN1 reaction as well. Okay, it can protonate this group right here. That's actually a pretty good leaving group, isn't it? Okay, and so then it could leave, generate the carbocation. And once we've generated carbocations, the gloves are off, right? super high energy intermediate. It can do all sorts of things. We could have attacks from either direction once we have a carbocation, right? And so all of a sudden our stereochemistry is a coin flip rather than being a known quantity. The other problem here is that when we generate carbocations, if there's a hydride shift or a methyl shift, what's going to be the more likely outcome? Hydride and methyl shifts, right? So we can't always target the carbon we want to target if we have the possibility of generating carbocations. Okay? So for example, this alcohol right here, which is next to this one, which is that tertiary carbon, we can't target this one, can we? The second we generate that dang carbocation, it's going to have a hydride shift, and we're going to end up attacking that one, aren't we? And so we'll never be able to get that other product. We're always going to end up getting that product instead. Okay? Okay, so how can we do this under gentler conditions that don't generate that dang carbocation? Okay, that don't have such a strong possibility of generating carbocations. Well, we can actually add something that will provide bromides in a much more reasonable concentration without generating that very reactive first group. And so PBr3 is one way of providing reactive bromides that will do this reaction. We'll use diethyl ether for our solvent. And this is going to do this. It will give us the specific specific inversion of that configuration, because instead of possibly generating carbocation, we're just going to do the SN2 reaction. Okay. The other thing is, if we just do the SN2 reaction, we also don't have to worry about any methyl shifts or hydride shifts, right? Because we don't generate the carbocation. Okay. Okay, so this right here is actually the mechanism, and this is why this works. So what happens is this phosphorus here, because of all those bromides on it, is very, very electron poor. Okay? I'm going to get rid of that arrow real quick, just so you guys don't get confused. Oh, wow. I froze the computer. And crashed the computer. Impressive. No. Oh, interesting. They've updated Slido apparently, and it's now super not stable. Okay. That's wonderful. All right, so again, this is the one right here. That phosphorus is very electron poor because it has all those bromides pulling electron density away from it. So what's going to end up happening is the OH, the oxygen, has that lone pair. That's an electron-rich group. And so the first thing that happens is it actually pulls the electron density away from the oxygen onto that phosphorus. Okay? This is going to bond the phosphorus here to that oxygen. Can everybody see that bond? Positively charged oxygen. Okay. So what happens next is by pulling the electron density off of the oxygen, it caused that Br to take the electron density from the phosphorus and leave. This generated negative Br in the solution. Okay? And so that negative Br can now act as our nucleophile, attacking that carbon here in an SN2 reaction. And we have generated this electron poor oxygen that's going to pull the electron density away from there. Okay? and that's then going to act as our leaving group. So essentially, we've added both a source of Br minus and our leaving group enabler, right? In one step. Pretty cool, huh? Nice symmetry to it. And so this is then going to be an SN2 reaction. If we have an SN2 reaction, what always happens to the geometry of our stereocenter? We always flip it, right? We have the inversion. Okay? And so we get the inverted geometry. By the way, this is actually the product right here. So yeah, it has the OH that took. Okay, so let's talk about some of the limitations of using PCl3 or PBr3. So the OH group is an sp2 hybridized carbon. We will never form the halide. Okay, and again, that's because of that resonance stabilization that happens there and the conjugate ring here. So excessive steric hindrance in a tertiary alcohol. What happens to the SN2 reaction when we have a tertiary alcohol or a tertiary anything?
It's very difficult for the reactor to go back.
Yeah, highly sterically hindered, right? So what we end up getting is an extremely poor yield. So poor of a yield that could you do this reaction? Maybe if you have enough time. But you might have to come back a week from now. Okay? We might have to run this reaction over break. All right. Not exactly something you want to do as a graduate student or somebody that actually has to accomplish something, right? Now let's predict the products of this reaction and draw its completion, detailed mechanism. Make sure you pay attention to the stereochemistry. So go ahead and start writing that. I'm going to give you a little quiz thing where I'm going to ask you what the product's going to be. And then we'll go ahead and do the rest of the mechanism. Oh my goodness, there's 2 alcohols. Which one do we attack? Okay.
You actually asked them
I mean, yeah, you gotta figure that out.
on the brain.
Yeah. Right. I'm gonna start moving on. So what will that product be? Oh, wow. Oh, we won't actually be able to do the Slido. Sorry. Yeah, Slido crashed on my computer. I need to figure out what's going on with that program. And maybe I have to get rid of Slido after I just paid their asses. That would be the way things are going for me this semester. Technology has not been my friend this semester. Which is unusual, because technology usually is. But, man. Alright. So, what sort of product are we looking at? We're going to substitute that alcohol, aren't we? What are we going to replace it with? Br, right? Bromide. Is it going to be fading into the paper or coming out towards you? Coming out towards us, yeah. And so, this is going to be your mechanism here. First step is going to be the oxygen's electrons going into a bond with that phosphorus, right? This is going to cause the Br on that phosphorus to leave. Notice that that's very, very SN2-like, right? Yeah, technically you could call that an SN2 reaction, yeah. And so once our bromide leaves, we're going to have this phosphorus bound to the oxygen, right? And that's then going to have the Br minus attacking that carbon and the oxygen leaving. Okay, anybody getting lost at all there? Okay, all right, and that's going to give us this product here. That would be the other product right there. Okay. Okay, so this then is the halogenation of the alpha carbons. Notice again, this is alpha carbon. This is the next carbon over. Can everybody see that okay? Okay. This right here would be our normal, like SN2 target, right? And that has the carbonyl on it. That's the one that's actually involved in the functional group. Okay. Okay. And so what we're going to see here is this is going to be a halogenation. We're going to target specifically the alpha carbon, the next one over. The reaction conditions for this is going to be Br2, and then that is in NaOH. So what sort of conditions do we have? We're basic, and we have Br2 available, right? Okay. Okay, and so the alpha carbons that we're going to target with this reaction are going to be the ones that are the alpha carbon of a ketone or aldehyde. This is going to involve treatment with Cl2, Br2, I2, but all of these ones are going to be under basic conditions. Okay, and so what we'll get then is we'll get a Br2 that attaches to this carbon here, which is the alpha. And notice that what gets lost here? The hydrogen right there, right? Okay. Okay. And that's very important that there's a hydrogen right there, right? Because that's actually what we're going to target in this reaction. Okay, so the first step we're going to actually do is in these reactions, that alpha carbon oftentimes was getting targeted for E1, E2 eliminations, right? Remember that? And so we're effectively doing something very similar to an E2 reaction, aren't we? Can everybody see that? We're attacking that alpha hydrogen, aren't we? With a strong base. Okay, and so that's the first step of this. We attack that alpha hydrogen with a strong base. In this case, it's going to cause the electrons to go up on that carbon. Now, what's next to this carbon in this case, though? A carbonyl, right? And so carbonyls can form resonance structures if you have a negative charge next to them. And so this gives us the enolate anion. This is enolate because it has the enol, right? I.e. a double bond with a carbonyl or oxygen next to it. Okay. Normally we would talk about that in terms of an alcohol next to a double bond. Okay. And so this can actually pull the electron density onto that positively charged carbon, and the electron density can get pulled up here onto the oxygen. And see how we're resonance stabilizing that negative charge there? Making it stable enough we can actually generate the intermediate. Okay. Okay, so the next step that's going to happen here is this negative charge on this carbon here is going to attack a Br, because Br bonded to another Br is neutral, isn't it? And bromide actually has a pretty good electronegativity. So it's going to attack this negative charge on the carbon. It's going to leave the bond over on the other Br. Notice that this is actually an SN2 style reaction, except it's reverse of what you normally think of it, right? Our carbon's actually the negative species here, right? That's then attacking a bromide, causing another bromide to leave. Okay? So it's kind of a reverse looking SN2, right? An unusual looking one. Okay. And so this generates the leaving group bromide here and attaches the bromide to that alpha carbon. Everybody okay with that? Anybody have any questions? Okay. Okay. So the alpha halogenation product, this can act as a new substrate. This is one of the reasons why I wanted to show you that reaction. It gives you a tool where you can then target the alpha carbon for a variety of different other purposes. Okay. And so, for example, if you put in a pretty good nucleophile into this, Well, bromide's a pretty good leaving group, right? And so now we can do a new SN2 reaction, can't we? Okay. And we can go ahead and swap bromide with another carbon, say, with another functional group, right? The other thing that we could do is we could put another powerful base in here and do the elimination. Because again, these hydrogens here are all going to be good targets for elimination, right? Okay. And so we can perform the elimination and generate double bonds. So notice we now have tools that we can continuously branch things out, make new structures. Ooh, ah. We're slowly getting our different colors to paint with, aren't we? Okay. So because of the polarizability of Br2, the approach of a nucleophile actually creates an induced dipole. So when we actually put a negative charge next to Br, those electrons very easily flow off onto the other Br. And so it creates this induced dipole, which is right here. Everybody see that okay? This actually sets up the electron rich to the electron poor driving force for the SN2 reaction. This is why, despite this not normally being like a positive charge on the Br, it's very easy to flow electrons along the Brs, and so it can induce that state instead. Okay? And this is how those can then be electron poor. This is the stereochemistry of the alpha halogenation. You'll notice that again, it was an SN2 reaction, meaning it maintains stereochemistry, doesn't it? Okay, and so we're going to actually end up sort of maintaining the stereochemistry to some degree via this. Okay, so let's step back. Okay. So what's going to end up happening is we're going to generate the first step here is we're going to go to this carbanion, right? Negative charge. And this is going to have this CH3. But when we have that, what's going to happen to the carbanion? Did those stay in hybridized orbitals whenever we were talking about those lone pairs? And negative charge? Normally, yes. But we have one additional step that I haven't written out yet, have we? What happens to that carbanion? Why is that stable? Why can that do that next attack and actually has time to do it? Yeah, the resonance structure, the inlay. This charge is going to get pulled up onto this oxygen, isn't it? And going to form a double bond. What happens with that structure? Yeah, it's more stable, but let me go back to the structure. What stereochemistry does that have? That's planar, isn't it? Yeah. And so what ends up happening here, due to that stabilization, is we actually do create a planar structure. This then can approach this bromide. And despite this being an SN2, this is one of the few times where we're actually going to end up with a mixture of stereochemistry. And that's because the SN2 is attacking the bromide, right? The bromide would be the one that would normally keep its stereochemistry, right? Does that help us? No, it doesn't help us. Okay? And so we end up with a mixture of stereoisomers here, but for kind of an interesting reason, right? And it's because the Br2 is the one that would technically preserve its stereochemistry, which does not help us. Okay. This is the polyhalogenation under basic conditions. So here we see that we actually have two different centers here that we could do this reaction on, except for one of them does not have any hydrogens, right? Can everybody say okay? Mm-hmm.
What was the difference between alpha and beta hydrogens again?
Alpha and beta hydrogens are the positions over. So for example, this one is beta. This one is alpha.
So it just depends on what carbon they're attached to?
Mm-hmm. So in this case right here, the alpha hydrogens are the next one over from that functional group, which is the carbonyl. Okay. And that's important because while we're pulling electron density away from them, we're also setting it up so we could stabilize the negatively charged carbon, their carbanion. Okay. Okay, and so in this case right here, we can actually do this reaction twice. Can everybody see that? That we can actually pull off two different hydrogens. Because there's going to be two hydrogens right here, right? Mm-hmm.
Is that just because it's a primary carbon cation? Like if there was a methyl group attached to it, then you would only do it one time?
Yeah.
Okay.
Yeah. If we had another methyl, we could only have one hydrogen possible. Yeah. You could technically do this on two different sides as well. So like if we had one less methyl here, we could do it on two different sides. But in this case, we're setting it up so we can double bromate. Put two bromos on there. Okay. Now, when you do this, however, there's an interesting phenomenon that happens. So for each halogen atom, what's going to happen to that charge for the carbon? It's going to become more positive, right? And so for each halogen atom you add, what ends up happening is that H becomes more and more acidic, actually. So this reaction actually speeds up as you add more bromines. Okay? And so you can't actually just get the single brominated here. What's going to happen is when you do the first bromine, that second one's actually going to happen faster. Okay? And this is actually the mechanism for that reaction. Again, you see that first step again, where we produce the enolate anion here. We'll attack it with the first bromine, and that's going to give us the single brominated, right? Now for the next one, this hydrogen here is more acidic. It's going to actually be even more acidic. It's going to be easier to pull that one off than it was the first time you do it. Okay? And so what ends up happening is we get the second enolate with the bromine on it, and that's going to end up doing the reaction again, even faster. Okay? Okay. And so what ends up happening is if you end up speeding up the reaction every time you brominate these. And if you have it set up so that you can double brominate, you're almost assured to double brominate. Okay? You're going to get the major product double brominated, not singularly brominated. Under acidic conditions, let's go ahead and check this out. If you do the similar reaction but under acidic conditions, which has a different first step, you're only going to do a single halogenation because the reaction will actually become slower as you add halogen atoms. Because each halogen atom is going to pull electron density away, right? Under the acidic conditions, we're actually going to generate carbocations. Okay? All right, so this is the acidic conditions. The first step for the acidic conditions is we actually protonate the oxygen. So see that? We're going to protonate the oxygen first. We're going to generate this right here, which is the positively charged oxygen there. Okay. And this is going to pull electron density away from that bond. What's going to happen next is we're actually going to have this group attack and pull that hydrogen here that's now acidic off. This is going to leave the electrons, which will then generate the enol. Okay. Can everybody see the enol okay? Okay. Okay. We're actually kind of doing a weird thing here. This is actually the direct product of that over here, okay?
So what's the point of moving the double bond to the lone pair? You're just going to move it back?
What it is it's the resonance structure. So this is actually the enol, which is where you get the name from. It's also the stabilizing factor here. But yeah, it's a little bit confusing because this directly would be here, right? Yeah. But yeah, that's the enal resonance structure right there. Okay. The easiest way to remember is that, honestly speaking, it doesn't actually matter which resonance structure you put as first, because a resonance structure series is an entire structure together, right? Yeah. Okay, and so from here on, it actually becomes the same reaction. It just has a very strange looking intermediate that has a positive and negative charge on it. Okay, and so again, you get the attack with the lone pair on the chlorine here, leaving the electrons on the other chlorine. This gives you then the product here. Note, however, we have to go ahead and do one more proton transfer for this reaction, which is going to be the attack by the remaining base, taking that hydrogen off. Okay, that's going to give us the halogenation. Notice the halogenation is not going to do a second one, because once we put a positive charge on that carbon, it's actually going to block it being able to give electron density, right? Okay. And so this reaction becomes slower and slower, actually. Okay. All right, so this is the epoxides as substrates. What we would do here is we are going to generate the epoxide. We can then use that as a reactive intermediate to do further reactions. Okay. Okay, I guess we're going to have to stop here because that's the end of the day. Okay.
Yeah, is are you gonna extend the chapter 10 homework so you can do all 10 right today?
Yeah, I'm going to have to. Yeah. Yeah, I'm going to have to figure out what I want to do with that. We're running a bit late, aren't we? Yeah, I have so much stuff I have to do. Yeah. Thanksgiving's going to be just nuts for me.
It's that time of the year where you're supposed to be the most relaxed, but you're actually busiest.
Oh, man.
But it's okay. You got this.
Yeah, I gotta get all the stuff for the classes, but I also have to figure out what I'm gonna do at the house. Yeah.
Goodness. A lot of life stuff too on top of that.
Yeah, Thanksgiving's crazy. You got a good Thanksgiving that's gonna come up?
Yeah, I think so. My family's in town, so it'll be fine. It'll either be really good or really bad. You know,
Okay. Well, I'm gonna hope it's really good.
Yeah, I'm always holding out hope for really good. See you later.
Good luck. Okay.
So we have a question. So for the lecture videos that does not have audio in that, would you be able to fix it or?
I won't. Yeah. What it did was it detected another microphone that wasn't actually recording, apparently.
So we're not able to fix it.
Yeah, I can't fix that at all, unfortunately.
Was it just one video?
It was about a week.